Hi, we are back now to uh, the next session that in the spreadsheet format. Okay, what you are seeing on your screen now, okay, is we call the classical diet problem. Okay, setting up under the uncertainty of the amount of nutrient in each raw material. Okay, uh, which I think that we express the uncertainty based on this highlight of the two uh, table here. Okay, the first one is according to the explanation is expected value for each amount of nutrient. Okay, digested from each raw material. Okay. Okay, in this case, we have 4 nutrients for consideration and with 5 raw materials, okay? And this is the number of each nutrient, okay, digested by each raw material, okay? And it's only the expected value. As I mentioned you before that this value in the original diet problem is assumed to be deterministic and well uh, set up as a constant with no uncertainty. But in the real world, okay, as you might know that when each raw material supply to your industry has a huge amount of lot size, okay, and certainly some of this quality of nutrient in each raw material cannot be controlled to be a constant value. It can only guarantee you or giving you what we call the within the tolerance limit. So this is the tolerance limit generated for each uncertain value of nutrient digested from each raw material. Okay, and this table here is a generation. Okay, if you look at this formula here, is the for each of this formula is used for the generation of each expected value plus or minus tolerance using the uniform distribution assumption here. Okay, and I'm gonna increase the size a little bit so you can see the formula here. Okay, so the first formula is that you have D7 here. D7 is the amount of nutrient number one generated by raw material number one. Okay, okay. The minus D5, the D15. D15 is the tolerance. Okay, so the mean minus the tolerance is a lower limit. Okay, at least, and then you plus the rounding value of random number uh, random variable, okay, of a uniform 0 and 1 multiplied by 2 times the 15. You remember that once you start from the minimum value, okay, at most you add up with 2 times the tolerance here because the tolerance is based on the mid value. Okay, so this one is to generate the value from the at least the amount of uh, the mean value, okay, the expected value here, okay, minus the tolerance that indicate the minimum value that can happen, plus at most it cannot be above 2 times the tolerance value. Okay, and this one is rounding for the accuracy of 3 digit, okay, the precision. Okay, and so therefore with the reference of the position of the formula, you can copy all of this to other element also. Okay, so this is the way we generate the scenario of uncertainty here. So what I did is that I just make a copy of this scenario generation and apply it to this one, to this value. Okay, the scenario for each tree. Okay, I highlight it with the alternate color. Okay, so let's see how many generation that we already, but you cannot see the formula here because once you generate it, I just copy back to the same location with just only the value to erase all the formula. But you can always come back and use this as a generation from scenario generation, okay, formula, and apply to to, or if you want to add more scenario for your analysis. As you see that based on the formula here, okay, the location of tolerance and expected value are all use the absolute addressing, so you can copy this to anywhere in your spreadsheet. Okay, and this is the model is that, okay, once you know you generate the number of scenario for each uh, nutrient in each raw material. Okay, and actually, you know, you can have a multi-million number of possible scenario, even for the precision of 3 digit. Okay, because you have so many uncertain element here. Okay, how many uncertainty element here? You can see it. 5 times 2, the 20 uncertain element. Okay, as compared to our previous example, which only 6. Okay, and even for the original paper of Dan 6 that we discussed on the previous clip, so only 1. Okay, with D2, if you might remember the demand of the customer. Okay, but this one you have 20. Okay, if each if you only generate only two possible alternative for each nutrient in raw material, you for total combination is already 2 to the 20. Okay, and certainly a large amount of scenario can be generated based on this combinatory nature. But in this case, let's see how many scenario that we generate in this worksheet. It's around 1,156 scenario. Okay, so I'm not gonna say that why. You can generate as much as possible because this problem is already solved. Okay, okay. I'm gonna explain the model, spreadsheet model a little bit. Okay, by passing the algebraic formula of the LP. Okay. Certainly, once you know for each scenario, once you know the amount of nutrient in each raw material, you can evaluate this cell. Okay, this column of G. Okay, is generate that. Okay, you want once you already make decision, look at the green highlight, the yellow highlight here. This is the amount of each raw material. Okay, we have 5 raw material. Okay, this is the decision of that how much within the one here. This is a summation for all value here is equal to 1. This is a explanation to to the problem that what is the proportion of each raw material in the 1 unit of the feed mix. Okay, this is a 1 unit of the feed mix. This is a proportion for each raw material. And each raw material you don't, and this is a cost per unit for each raw material based on the reference one or from the raw material one. That's why we give raw material one the cost of 1 unit. Raw material 2 is about 1.5 of raw material 1. Raw material 3 is only 90% based on the cost per unit of raw material 1. So this is a relative cost here. Okay, and also look at in reality that, okay, if you want to minimize the cost, this is the cost of minimizing. You use some. This is for the deterministic cost is only the cost per unit. The sum product of these two set of changing cell. Okay, you're gonna get, but not including the stochastic cost. But once you make a decision here, let's say x1 to x5, the amount of raw material in the feed mix, okay, and you unitize it by this constraint that this summation is equal to 1. But is that enough? Okay, you look in the real world when we're talking about the diet or the recipe formula, even we as a human nature, okay, we always prefer what we call the recipe. That, okay, we don't really consider the cost that much. If that we more concerned about the taste. Okay, you can eat a lot when tastes good. Okay, okay, and but even though you can have a minimum cost diet. Okay, animal is the same as human, that they're not going to take it if you just keep adding the cheap stuff in your feed mix. Like in this case, it might be the raw material number 3 because it's the cheapest one. Okay, But if you put it in too much, it might actually save your cost, but the resulting solution might not be acceptable by the animal who type that you're going to feed them. So in the classic of the diet problem, this is a very top secret of for each feed meat industry. We call recipe. Okay, so for each raw material, okay, they will have some recipe that okay, but for a raw material number one, you don't need to include it. You don't want to, but at most you cannot add in one unit of feed meat no more than 15%. Okay, raw material two, at least you have to put it in 10%. Okay, you cannot avoid, even the is the most expensive one, you need to add it 10%, at most no more than 40%. Okay, raw material 3 also. So this one is at least as most, is mean that it's a bounded variable constraint for each decision variable, that and is applicable for the diet problem because it's a recipe and it's very highly sensitive with the total cost that you're gonna get. Okay, if you don't know this value for good, okay, you might end up producing something that your animal will not take. Okay, but if you put this a little bit more, you know, tasty condition to make your food more tasty, you might end up having increase the cost per unit, and also is the food is might be over expense. Okay, and the animal, even though you're the customer and you might want to take this, just like we all, that we love expensive foods which taste very good. Okay, but in the case of the diet problem, you want the cheapest food with the tasty for your customer also. Okay, so this is a solution we already found at this moment. Okay, this is the 15%, this one 33.684%, and also altogether is equal to 1. So you can see that we have a constraint that related to the uncertain here. Okay, this is just like the A matrix here. Okay, this is the X, but in this case we have an additional constraint of the bounded variable here. Okay, we have X is greater than or less than or equal both on both sides, the finite bound. Okay, but this one is already automatic, x1 more than or equal to 0, but the remaining x you have additional constraint. Okay, so this one is an additional constraint, and you also have an additional constraint of summation of x1 plus x2 plus x3 plus x4 plus x5 have to be equal to 1, and this is not the type of any, have nothing to do with any scenario. Okay, but it have a lot to do when you want to find a new x here. Okay, so we are doing the same thing as we in the previous example, that actually we need a times x. This is a. Okay, this is a nutrient evaluation. Instead of you using metric, you use a summation of each row to each row, and then you can fix the address of the amount of each raw material and then make a copy. This one we call this the nutrient evaluation, or this one part is the evaluation of a times x. Okay, and you're now having a constraint of your, this is a quality constraint for each nutrient from your feed mix, that okay, in this case you will say that okay, for 1 unit of your feed mix, okay, once your feeding animal take it, okay, you expect that the first nutrient have to be between 14.9, at most it's 15. Okay, unit. AL is mean at least, AM abbreviation of at most. Okay, so this is the 4 requirement of quality of nutrient for your feed mix, and it's the same for each scenario. Okay, so this 4 part, okay, at least as most, is the same for all scenario that you are generated here. Okay, until your last one, 14 point to this one. Okay, so this is the requirement which is certain. Okay, based upon the standard of your feeding type. Okay, but your nutrient evaluation based on X here that you make decision can be, you know, have in this case have 1156 scenario come up. And each scenario, okay, it has some risky thing that it might be violated the at least constraint or at most constraint. Okay, so in this case, the problem is a little bit different than the previous one that we were using. For, for once is that once the uncertain for each nutrient here, okay, there are two constraints we need to evaluate, at least and at most here, okay, at least and at most, okay, which means that if nutrient evaluation in column Q here, okay, based on the uncertain amount of the nutrient for each raw material, no matter how good you make a decision here for the proportion of the feed mix for each raw material, okay, you end up going to have some risky condition for each condition that each nutrient cannot satisfy at least or the lower limit or at most, which means that exceed the upper limit here. Okay, so there's two constraints for one constraint of uncertainty for each nutrient. That's why we need to add two type of UV here. Okay, the first UV is for the at least equation, when you want to try to balance the at least constraint, and U and V here for AM, the bracket AM here is for the at most constraint. So you now can be realized that the metric here in uh, the metric that show in the Excel here is only half one. Okay, the actual is that one line here is equal to, you need to repeat it twice, okay, and repeat it one more time to have the size of the metric have to be twice larger than the one that present you in the spreadsheet. But with the spreadsheet nature, you don't have to worry about it, because you can have the evaluation, you can save, you don't need to put this table repeated again, okay. And but UV will indicate to you that now you have UV for the type of, for the right hand side of at least, and U and V for the right hand side of at most, based on this nutrient evaluation. Okay, so we put the formula of U and V here. Okay, the same is once you have UAL, okay, you have, in this case, once we make decision here, the nutrient evaluation here, okay, 14.8 is less than at least, which is now the risky condition. So that's why you have UAL here, because this one is less than this one. Okay, and also you don't have VAL because you this one is less than this one. Okay, but you have UAM because this one is less than this one. Certainly it's not going to less than this one. But UAM and VAL, you can see that there's no additional cost in this moment, because you need to have an additional cost when what? When your nutrient evaluation have in scenario that violate the at least constraint, and also the other, which is the U value, UAL value, and another one is happen here. Okay, down here. Okay, in the third nutrient tree, 13.27974 is exceeding this. So even though it's already okay, meet this constraint, at least, okay, it's over 13, it's okay, so it's feasible, but it's over here, but so that's why you need VAL to balance it minus, but this VAL have no cost because it's feasible here, the cost is zero here. Okay, but the VAM here, okay, because it's exceed 13.2 exceed by 0.07, this one have the cost additional. That's why even we add U and V on both at least and at most the right hand side here, okay, to balance the equation. Okay, only UAL and VAM have what we call additional cost, stochastic cost here, and that resulting to the identification of the target cell down here. But first of all, okay, you have to understand that we generate what we call the corrective action cost. This is the cost per unit of G and H, okay, and it have a non-zero value for only UAL and VAM. As I already explained that VAL and UAM you have no additional cost here, okay, and you don't need to set them to become zero at the end. It's not artificial variable. Let me tell you, it's not artificial variable, okay, because once you have value V0, once we have value U0, so it's not artificial variable, okay. So this is a collective action cost. So what does it mean for this U and H down here, okay. Let's look at the formula here for G. Okay, it's 1 divided by the number. This is the number of scenario J. I will show you. This one for H is 1.1. Okay, so you might wonder how 1 and 1.1 coming. For the second one is 1.2 and 0.95. Okay, so but all together, okay, divided by J here. Okay, this one J 4,628 down here. Okay, 1,000. This is the number of scenario that we consider in this model. Okay. You might wonder how I'm trying to generate the G and H that different than from our early example where we use a constant G and H for all. But this one you can see that for each row and for each nutrient, okay, to make a collective action for each nutrient, they should differentiate the cost per unit for each nutrient, okay. That we should, and this one I didn't put it in separately to show you, but you have to take a look at this formula. Like in nutrient number 1, suppose that the corrective action cost is 1 unit, okay, and if the uniform distribution, so you need to divide it by number of scenario to get the expected cost. For H value is allowed 10% more than G, okay, which means that in this case you want to have an underachievement over rather than the achievement of the right hand side, because you want U, you don't want V. V is when your left hand side is greater than the right hand side, okay, to balance it. And this one is different, that okay, this one become 1.2, but this one is 0.95, okay. So it means, so the second one you see that the first one 1 and 1.1, so H is more, but in this one you rather have H value for nutrient number 2, so that it can contradict each other, okay, and the obvious or the trivial solution cannot be detected, okay. So the nutrient T is 105, okay, and 0.975, and nutrient 4 is 1.25 and 0.98, okay, and then the number repeated again, okay, for each one of this, okay. So this 4, okay, and this 4, okay, keep repeating itself for each scenario, okay, the same. This is how you get the result G and H. And once you get this one, you need to make this to sum product. This one need to make a sum product with U, and HVM is sum product with V, and there's nothing to do because the cost coefficient of VAL and UAM is 0. Okay, so this is how we end up having the total cost here. The deterministic cost is L4, this one, this two, L4 and P4 and L5, P5. The cost per unit for each raw material and the amount allocated for each raw material in the feed mix. But then the stochastic cost is here, the sum product of T7 to T4630, which is the T is the UAL. With the X, you can see X here. X is a column of cost of UAL. And the same for here. Okay, for V and Y, okay. Since V is W here, okay, it's VAM, okay, and cost per unit is in the Y column here. Okay, so that's sum it up for the total cost based on Danzig's expected cost function. Okay, once you already have G and H here, you can evaluate A times X is I think that it's obvious. That's the mathematics. It's the same as net nutrient evaluation here. These two columns have the same value, Q and column C here. Okay, and you can know that now you need to have a Y. Okay, for two type. Okay, when right hand side according to at least constraint and right hand side according to at most constraint. So you have to Y corresponding dual variable here for Y at least and Y at most here. So the easiest way is to check out, okay, that if UAL have a positive value, okay, so you pick with the G value. You remember that for when you're under achievement, you get you take the maximum value as much as G. But when V value is effective, like VAM here, when VAM effective, okay. If the V and U is not within U and VAM here, okay. So both dual variable according to that constraint is 0. But once you have VAM, it's a violation already. You need to add more VAM. Now you use the minus H here. This one, okay. You remember that all Y greater at most cannot exceed the G vector, and for each Y at least have to be greater than or equal to minus H for the sub problem when you already originate the X value here. Okay, so this is how the results come out. Okay, well, once you get the X and you get the new Y here. Okay, with the new Y here, you're gonna get what we call here the bender cut. This one have already been done 10 times. Okay, we start from the first solution, and I already attached the solution here. We start solution here first, the first 5 solution here, and then you get the initial T value. This is a T value. Okay, T value is here, the target cell for the sub problem. As you can see that you can easily use the direct solver. You don't need any what we call the open solver, because we already eliminate the value of U and V here, okay, based on the decomposition. So in each round you need a bender cut over here. Okay, this one already done by 10 iteration. Okay, for each iteration, and you know that the first equation is the one that generate the cut. The formula is all here. Okay, the formula is all here. Okay, I will explain the formula a little bit for you to make you understand better. Okay, the formula is only here, so the new cut is here. Okay, and this one is the cut, and the previous cut, okay, already they accept. We make a copy just like what we did in the previous example. Copy it down, copy it down. So this is the new cut already. Okay, that we have here, and it already solved. You get this solution here. Okay, and now you get what we call the decision of 1.446.163. This is, and we going back and look at the optimum solution now. Now you can see that this is the same. Now the total cost here, this is the upper limit, okay, but the lower limit is still not equal. It's different on the third digit. It's only 1.441. To make sure that it is equal, you need to achieve the T value equal to 1.446 down here. Okay, so this is the what we did so far here. Okay, and we solve this solution. We get the new solution already here. Okay, and this solution is not having been replaced here yet. This one is still the solution, the last solution that you found here, the 10th solution here. Okay, and suppose I'm going to do it one iteration for you. Okay, that we are going to do. First of all, we need to move this one down here to cut number 11. Okay, And then for raw material 1 to 5 here, okay, with the previous cut, we need to copy it, and then we need to paste just the value, okay, and then we can make a copy of the formula here, okay, to this one also, okay, and then make a copy of the right hand side, just the value, okay, we make a copy, and then we have just put the value here, okay. So now we move the previous cut, the 10 cut, to cut number 2 to cut number 11, and then we can okay, make a border for the table. So and also we have to move all of this, okay, raw material, the 5 raw material down here. We need to make a copy, and then we need just paste the value here, okay. Okay, just paste the value. But this one, if you want to put the color on, you can do it, okay. This one, and then this one, okay, you can put this color on, okay, the same color, okay, and then you can make a boundary, okay. So in this case, okay, we already moved down it. You don't need anything here anymore, okay, and this one is already you can create, okay, the content. So now all the solution and that generate for the previous cut, okay, this is the previous the best solution that we found so far here. This is not the t value, sorry, this is this column is according to the upper limit here, the best solution that we found so far, okay. You can see that this is the minimum one that we found so far. This is a previous solution that we found. Some iteration they get a worse solution from iteration to next iteration. Yes, but eventually it's going to converge because the upper bound keep increasing. Okay, so we're now ready here. Okay, that we need to put, this is the new solution that we already found, the latest one. Okay, so I'm going to make a copy here, okay, and put it in here. Okay, I put this one. This is the value of the optimum solution, the new one, the newest one here. And we're gonna generate the new cut here. The cut one will regenerate if I put this solution here. Okay, I'm gonna put the solution here. Okay, so now we get the new solution. It becomes 1.448, which is worse than the previous one, 1.446. But we're gonna use it here. So I make a copy here, okay, of the current solution down here. This is the solution based on this the current solution, the latest solution that we found. So in this one we just put the value here. So this is the one, this is the upper bound, but the best solution is still here. Okay, the best solution is still on the one that I make a highlight, the latest highlight here. Okay, 1.4613. This one is not the better solution, but with this, you remember that once we put the new solution here, the new x, we get the new one, the new of y value here, the y. This is the new y value, and with the new y value, they generate the new cut here. Okay, the cut, and the new cut is always invisible. You can see that minus, left hand side minus 18.6189, but the right hand side is minus 18.612. This one must be, left hand side must be greater than the right hand side according to the cut equation, optimality cut equation in Bender decomposition. So you know that with additional cut here, this if we rerun this problem again, we get the new x, and certainly we're gonna have what, the higher t value. Hopefully the new t value will reach this part, okay, of the best decision here. We see how the results come up. Okay, first of all, I need to go back and then go to the solver again. With the solver routine, okay, you need to rearrange this by deleting the previous constraint here, and then we add, okay, now we need have additional one, become 11 constraint here. Left hand side is greater than or equal to the right hand side down here. Okay, but I want you to observe that we to control to find the new x by solving this problem, we have to make sure that ag5 is equal to 1, which is this one, the constraint here, that we need to make sure that the summation here is equal to 1. Okay, ag5, or no, this is k is on this cell, but ag is down here. Okay, here, sorry. We have to make sure that raw material here is equal to 1. And we also need to make sure that the changing cell here, the AH5 to AL5, okay, here, okay, these two, have to be within the recipe constraint, which is the at least and at most here. Okay, at least and at most here. Okay, so make sure that you understand that this is an additional constraint beyond the previous one that we already solved in the previous example. Okay, because to find a new x, sometimes you have an additional constraint. Okay, additional constraint. This one we already add this requirement for the x here, and the target cell is still here, AH3. Certainly we want to minimize this according to with a new cut constraint using simplex we solve it. Okay, okay, I got this one. Okay, let's see how the result come out. Oh, very stubborn here, 1.442889. okay, but it's at least greater than the previous one. 1.441. okay, the t increasing, but still cannot verify the optimality here. Okay, the optimum solution down here is still not verified because the best solution is still 1.446. Okay, so there's some duality gap between around 0.004. Okay, unit. So okay, so I think that I show you enough from the previous example with this one. You should be able to continue solving this by yourself, okay, to verify the optimality. Let me tell you that you're not going to exceed 20 cut. You get the verification up to the third or fourth digit of the optimum solution, okay, which is lower than the previous example when we need to take up to 80 cut, if you might remember, or even we solve under the MATLAB routine, take more than 50 or 60 cut, okay, in other words, in iteration also. Okay, I'm gonna end this part. Okay, for you, if you might not be able to follow in some part, you can rewatch it again. Okay, but you should continue working this iteration by iteration until reaching the concept that the t value is close to the optimum solution found. Okay, comparing to all iteration, okay, that you generate the new x. Okay, pick the best one, pick the minimum one. In this case, it's this one. Okay, this one is the minimum. Okay, you should continue this by yourself. Okay, working on this worksheet, and also I would like to encourage you, okay, to using the scenario generation here. Okay, here. Adding more scenario, because in this case we generate only 1156 scenario. As you may know from the previous example that we illustrate to you, that the more scenario you generate, the closer to the population value, okay, as compared to, in this case, what we are doing, we just do a sample part. Okay, we only use the sample size of 1156. Okay, you should add more and more until you found the convergence of the population objective function, and also the convergence of the solution of the proportion for each raw material in the feed mix. Okay, we're going to continue look at this in the next clip. Okay, and we'll try to change, okay, the platform, spreadsheet platform, move to the MATLAB platform that we already developed. Okay, in the next step. Okay. Okay. So this session is end for now. Okay. See you in the next one.